Hey everybody, let's look at this one here. We got a Torricelli's problem it's going to ultimately turn out to be. It says that we have a 20-meter high dam right here, so this is 20 meters, is used to create a large lake over here. The lake is filled to a depth of 16 meters right there as shown above. The density of water, in case you forget, is 1,000 kilograms per cubic meter. Calculate the absolute pressure on the bottom of the lake next to the dam. So like right down here, what would be the pressure there? By the way, it's sort of not indicated in this one, but you want to imagine that this isn't plugged out yet because that could affect the pressure down there theoretically. But that little valve gets opened up later in the problem here. So it's pretty easy to find the absolute pressure. The absolute pressure is simply the atmospheric pressure plus the density of the fluid you're in times gravity times the depth that you are down in that fluid. And so all we got to do is simply plug in for each of these values. The absolute, or sorry, not the absolute, the atmospheric pressure is 100,000 pascals. We'll add to that the density of water, which is 1,000 kilograms per cubic meter. Gravity is 10 meters per second squared. And the height is 16 meters down at the bottom there. So if we multiply these out, we'll get 160,000. Add that to the 100,000 of air pressure, and we will get an absolute pressure of 260,000 pascals. All right, now let's move on to the other one. I'm going to keep this picture here handy because we're going to need it later on. It says a release valve is open 5 meters above the base of the dam and water exits horizontally from the valve. That's going to become important in the next part there. So here we are 5 meters from the base right here. And so calculate the initial speed of the water as it exits the valve right here. Let's call this 0.2. And let's call up here where the water begins 0.1. And so anytime we got water shooting horizontally out of a container like this, then we're going to be doing a Torricelli's problem. And to do that, we need to start with Bernoulli's equation here. And they insist that you write it all out. So let's start it. Pressure at 0.1 plus density times gravity times the height at 0.1 plus 1/2 times density times the velocity at 0.1 squared has got to equal the pressure at 0.2 plus density times gravity times the height at 0.2 plus 1/2 times density times the velocity at 0.2 squared. Ugh. Okay, but things start to simplify here a little bit. One thing to keep in mind is the pressures. Both at 0.1 and at 0.2, we are open to the air. So both of those are atmospheric pressure, both here and here. And since we're adding that same amount on each side of the equation, we can just get rid of that. The other thing is, as in all these Torricelli problems, is that we will imagine that this lake is so big that the water pouring out of here doesn't really affect the height here. So the water's just sitting here. So it doesn't have any velocity. So that means on what I've called side 1, we can get rid of that because that velocity is 0. And that simplifies things greatly for us here. Oh, and one more thing is whatever's left over, this term, this term, and this term, they all have a density. So we can calculate or cancel out that density in each of those terms. And that leaves us with this. G times H1 is equal to G times H2 plus 1/2 times velocity 2 squared. Let's subtract this term over to the other side there. And so we get, G times H1 minus G times H2 is equal to 1/2 times V2 squared. And then finally, let's get to the thing that we should basically have memorized. I'm going to do multiple steps at once. First thing I'm going to do is multiply a 2 over to this side. So 2, I'm going to factor a g out of these two terms. So 2 times g times the quantity H1 minus H2. And lastly, this is V2 squared. So I need to take a square root of all of that. And all of that is equal to V2. And so we can plug in for all of these values. So 2 times 10, and H1 minus H2, be careful here that you put this in, so it's 16 minus 5. And so in other words, we want the difference from here to here, which is 11. So 16 minus 5, and then if you work all of that algebra out there, you will get roughly 14.8 meters per second, depending upon where you've rounded. Okay, now, next part, they love pairing Torricelli's problem, which is what I would call this. And remember, as I said before, you must start with Bernoulli's equation and then derive Torricelli's equation, which is this. They love pairing this with a horizontal projectile problem. Also good practice to remember, if we do a horizontal projectile problem, to show where we get the equation. So they say the stream's 2 meters deep, so right here. And we shoot it out here. So the key thing to realize is that it drops 3 meters from the stream down to where it hits the water again. So that is our height. So in all horizontal projectile problems, we want to start with what we call the third kinematic equation, that our change in y position is equal to the initial y velocity times time plus 1/2 times the y acceleration times time squared. Remember, the y acceleration is g, and the initial y velocity for a horizontal projectile is 0. So that part is gone. When we rearrange this equation, we will get t is equal to 2 times the height over g, square root of all of that. You will have to show this derivation. On a multiple choice, you should have this equation memorized. So let's then plug in for here. We get 2 times the height is 3 meters and g is 10. Those are both technically negatives. And so that will give me a time of roughly 0.77 seconds there. Now, we can use that to figure out how far we go to the side. So our horizontal displacement will be our horizontal velocity times time. There is no horizontal acceleration, so we will plug in there. Our horizontal velocity is what we solved from Torricelli's equation. So 14.8 meters per second. We've got 0.77 seconds to fall, and so when we multiply those two out, we will get roughly 11.4 meters there. All right, last part here quickly. It says, suppose that atmospheric pressure in the vicinity of the dam increased, like some, some heavy, in a high pressure system moves in there. How would this affect the initial speed of the water as it exits the valve? Well, when we started this problem, the atmospheric pressure, we canceled that out because it was on both sides of the equation. So it doesn't matter what its value is. So when we come back to here, that horizontal velocity would remain the same. And the reason for that is we canceled pressure. So no effect. Exclamation point, exclamation point, exclamation point.